Now I'm going to discuss a small concept, that is spherical, conical and compound pendulum. First I am taking spherical pendulum. So what is a spherical pendulum? Here I will draw the figure of a spherical pendulum. Here this is the middle point of this sphere and I am calling it as A, and this is our spherical pendulum. A bob is here and it can oscillate in any direction. It can change its theta value, it can change its phi value, but radius r is constant, that is r equal to r. That is, for a spherical pendulum, r value will be constant, but theta value will not be a constant, and also phi value also not constant. This is the condition for a spherical pendulum. And we know for a spherical polar coordinate system, the general expression for Lagrangian is half m r dot square plus r square theta dot square plus r square sine square theta phi dot square minus v. Here you see r dot. Here we know r is a constant value, so r dot will be equal to 0. So for a spherical pendulum, in the Lagrangian of a spherical pendulum, r dot term will not be there. So what is the Lagrangian for a spherical pendulum? It will be 1 by 2m. Here I am taking this r as capital R, so it is r square theta dot square plus r square sine square theta phi dot square minus v. And here what is this v value? See, this is our spherical pendulum. Mass m, and it can rotate like this. That is, here its theta value is varying, so after some time the bob will be here, so its phi value is varying, and here this theta value is also varying. And if the length of the string is r, then this will be equal to r cos theta. And if we are taking this as 0, 0 reference point, then it will be minus r cos theta. And you know, this bob is oscillating under gravitational force, so the potential is gravitational potential, so we get the final Lagrangian as 1 by 2 m r square theta dot square plus r square sine square theta phi dot square minus mg h. So it will be plus mg r cos theta. So this is the Lagrangian for a spherical pendulum. So in general, for spherical polar coordinate, the general expression for Lagrangian is half m r dot square plus r square theta dot square plus r square sine square theta phi dot square minus v. And in this equation, if r equal to r and it is a constant value, then we will get spherical pendulum. That is L equal to 1 by 2 m, and here this r dot term is 0, therefore r square theta dot square plus r square sine square theta phi dot square plus mg r cos theta. This is for spherical pendulum. Now I am taking some special cases. Suppose r is a constant and I am taking theta also as a constant. Then I will get a conical pendulum. What is it? It will be like this one. Here it is oscillating at a constant theta angle. See, this angle theta will be a constant one. And here this r is also constant. Length of the pendulum is also constant. That is a conical pendulum. Now I am taking another condition, that is r equal to constant and phi equal to constant. Then I will get a simple pendulum. See, it oscillates like this. So here r is constant and phi is also constant. Theta is the only variable. So what will be the Lagrangian for conical pendulum? It will be equal to, here you see, theta is constant. So theta dot term will not be there. So we get L is equal to 1 by 2 m r square sin square theta phi dot square plus mg r cos theta. And what will be the Lagrangian for simple pendulum? It will be L equal to, here r is constant and phi is also constant. So this term will not be there. So we get L is equal to 1 by 2 m r square theta dot square plus mg r cos theta. Another example problem. Here this example problem I solve in 3 different ways. The problem is to find out Lagrangian of a spherical pendulum. What is its Lagrangian? That is the question. And Lagrangian is equal to t minus v, and you already know how to find out potential of a system. So in this discussion I will tell how to find out kinetic energy only, because you know already what is the potential of the system. Okay, so what is our spherical pendulum? This is our spherical pendulum. It's a bob of mass m and it can rotate like this, and it can rotate in this way also. So this is our axis. Okay, so this rotation about, this is z axis and this rotation is omega. Here this one is our 0 0 origin and this distance is r, that is the length of the pendulum, and here this angle is theta. Here you can see there are two motions. One is pendulum is oscillating in this direction and it is rotating about z axis with a angular velocity omega. So first I am solving this problem by using +2 physics. So what is kinetic energy? Kinetic energy may be of two types. Translational kinetic energy is there and the rotational kinetic energy is there. So here I am considering the rotational kinetic energy because this particle is in a rotation motion. And there are two rotations. One is rotation about 0, 0. See this one. The body is rotating about 0, 0. Another rotation is rotation about Z axis. That is this rotation. See, this one is rotation about origin 0, 0. This is the bob of mass m and its radius is r. And this bob is rotating in this direction. Okay. So what is the rotational kinetic energy? It is equal to half I omega square. Here, what is the I value? I value is equal to m r perpendicular square, and here it is equal to m r square. This is the plus 2 physics only, right? So we get kinetic energy T equal to 1 by 2 m r square omega square. Now I am considering the another rotation motion, that is rotation about Z axis. So here this is our origin 0, 0 position, and this is our bob m. And you know this is distance r, and this I am taking as angle theta. Then what will be the rotational kinetic energy here? Again it is half I omega square. And here what is the value of I? I is equal to mr perpendicular square, that is perpendicular distance from the axis. So this is the r perpendicular, that is equal to r sin theta. So what we get? We get T equal to half m r square sin square theta omega square. And what is the total kinetic energy? Total kinetic energy will be 1 by 2 m r square omega square plus half m r square sin square theta omega square. This is the total kinetic energy of the system. Here we can easily add these two values because these are scalars. That is why we are using Lagrangian mechanics. In Lagrangian mechanics, we are dealing with kinetic energy and potential energy, and these quantities are scalar values, so we can easily add. But in Newtonian mechanics, all are vector quantities. Velocity vector is there. So adding this velocity vector is a little difficult thing. But here you can easily add these values, kinetic energy or potential energy. So here you got the kinetic energy, and you can easily find out the potential energy. So you can write the Lagrangian for the system, that is kinetic energy minus potential energy. So write it here. It's a work for you. Now I am going to solve this problem by the second method, that is generalized equations. Here, from the symmetry of the system, we can find out the best coordinate is spherical polar coordinate system. So in spherical polar coordinate system, we know the general form of kinetic energy, that is T equal to 1 by 2 m r dot square plus r square theta dot square plus r square sin square theta phi dot square. Here you have to check which coordinates are varying with respect to time. Here you can see r equal to a constant value, and theta is not a constant value, and phi is also not a constant value. Therefore, r dot value will be equal to 0. So what we get? We get T equal to 1 by 2 m r square theta dot square plus r square sin square theta phi dot square. And here this theta dot is nothing but omega, and phi dot is also omega. Maybe you can call it as omega 1 and omega 2. Anyway, it is angular velocities because here angles are varying with respect to time. If both are same, that is phi dot and theta dot are same, then we can call them as omega omega. So we get t equal to 1 by 2 m r square omega square plus r square sine square theta omega square. The same thing we got by using plus 2 physics also. Okay, so you don't want to remember this general equation. If you know the basic physics, plus 2 physics, you can solve this problem. Now the third method, that is superposition. Here you should know about velocity element. Here also you can see the problem is in a spherical polar coordinate system. Or we can say the problem has certain spherical symmetry, so it is better to use spherical polar coordinate system. And in spherical polar coordinate system, the velocity elements are r dot, r theta dot, r sine theta, phi dot. Now we have to check what are the velocities. Here if it is rotating in this direction, then there will be a velocity, that is v1, and it will be equal to r theta dot. And you can see this mass is rotating about z axis, so there will be a velocity vector which is in the direction into the plane of paper. Okay, so this velocity vector v2 will be equal to r sine theta omega, because this perpendicular distance is r sine theta. Therefore the velocity v now v is equal to r omega. Here this r is r sine theta, so velocity, linear velocity will be r sine theta omega. And you can see the angle between v1 and v2, and that is equal to 90 degrees. So the total velocity v square will be equal to v1 square plus v2 square, that is equal to r square theta dot square plus r square sine square theta omega square. So we get kinetic energy T as 1 by 2 m r square theta dot square plus r square sine square theta omega square. Here theta dot is omega, so we get Lagrangian L is equal to 1 by 2 m r square omega square plus r square sine square theta omega square. And here this omega is corresponds to theta, and this is omega is corresponds to phi value. Okay, so see, you can solve this problem by using any method. So even if you know only plus 2 physics, then also you can solve this kind of problems. Another example problem. Here one disk is there, and this disk is rotating with a angular velocity omega, and the total mass of this disk is capital M, and a bob is attached to it, bob of mass M, and its length is L, and this angle is theta. Now find out the kinetic energy and potential energy and Lagrangian. This is the question. Here I am going to use the superposition method. You can use any method. I told you 3 methods. You can use any method to solve this problem, but here I am using superposition principle. Here there are 2 masses. One is capital M. So first I am considering this capital M. And what is the velocity of this capital M? Here this is the center of mass of this mass capital M, and when this disk is rotating with an angular velocity omega, it will travels in the forward direction. and this velocity v1 will be equal to r omega. I told you this point will move backward with a velocity r omega. So the center of mass point also will move in the forward direction with the same velocity, that is v1 equal to r omega. Obviously here the radius is r. So I get the kinetic energy T as half m r square omega square. Now what is the potential energy? For finding the potential energy, we have to choose the origin. So here I am choosing this point as origin. So this is my positive y axis and this is my minus y axis. Now what is the potential energy? Here the center of mass is at the origin, so potential energy will be equal to 0. So we get the Lagrangian for this mass itself is 1 by 2 m r square omega square. Now I am going to consider the small mass m, and here you can see the small mass m is attached to the disk. So when the disk is moving with a velocity v1 equal to r omega, this mass also will move, that is v1 is equal to r omega, and here it is rotating about the axis. So there is an additional velocity, that is this one, that is v2 equal to, this length is l and l theta dot, and the angle between these two velocities is theta. So we get v square equal to v1 square plus v2 square plus 2 v1 v2 cos theta, that is v square is equal to v1 square, that is r square omega square plus l square theta dot square plus 2 r omega l theta dot cos theta. So we can find out kinetic energy T is equal to 1 by 2 m r square omega square plus l square theta dot square plus 2 r omega l theta dot cos theta. Now we have to find out the potential energy V, and here you see this is the y, and this y value is equal to L cos theta. So V is equal to mg h, that is mg y, that is equal to mg L cos theta, and here this y is in the negative coordinate, therefore minus. So we can write the Lagrangian, that is Lagrangian equal to 1 by 2 m r square omega square plus l square theta dot square plus 2 r omega l theta dot cos theta. That is the total Lagrangian is, so suppose this is L1 and this is L2, then total Lagrangian is equal to L1 plus L2. So this is the Lagrangian corresponds to this entire system. Now you can see how easily we can solve with the superposition principle. Just look into the problem, write the equation. Okay. And this method is much more easier when options are there. You just cross check with the options. So you can solve this kind of problems within seconds. That is the advantage of this method. Okay. Here a small work for you. The work is to find out equations of motion for all the generalized coordinates. So first you have to identify what are the generalized coordinates, then you have to solve for equations of motion. Okay, this one is a work for you. This one is a system of pulleys. Okay, and a pendulum is oscillating with an angle theta, and the length of this pendulum is r, and the distance between these two pulleys is d, and this distance is y. And the total length of this string L is equal to y plus d plus r. And here I tell you this d is a constant value and L is also a constant value. Now you have to find out degrees of freedom of this system and Lagrangian of this system and equations of motion. Okay, please solve this problem right now. Now we are going to discuss another concept. It is central force. The motion under central force. A central force can be represented as F of r equal to F of r cap. See, the direction of force acting is in the same direction as its position vector. This is one of the main feature of central force. And this force may be of two types. Maybe it is positive. Positive means it will be repulsive. And maybe this F of r is a negative value. That means this force is an attractive force. And what will be the trajectory of a particle moving under central force? It will be a plane curve. What is this plane curve? Suppose this is a plane, x and y plane, and a particle is moving like this. Then we need only two parameters to represent it. That is, one is r and one is theta. So this is a plane curve. So under central force, a particle or a body will move only in a plane. That is, its motion is restricted to a plane if the force is a central force. Okay. And another property of central force is it will be a conservative force. What is a conservative force? The work done will be independent of path. And its consequence is total work done in a closed loop will be equal to 0. I'll tell you an example. This is our Earth and we have a particle or a ball at this position and we are taking this ball to little height. Then again we bring back to its initial position. Then the total work done will be equal to 0. So mathematically we can represent this condition as integral f dl equal to 0. And this circle means it is over a closed loop. Integral over a closed loop. And by applying the Stokes theorem, and some mathematical manipulations, I can write this equation in another form, that is F equal to minus del V, where V is potential energy. And this is the differential form of this condition and I can write its integral form. The integral form is V is equal to minus integral f dot dl and the integral limit from reference point to r. Most of the time the reference point may be infinity. And these equations are valid for a central force. Some examples for central force. First one is gravitational force. You know gravitational force F is equal to G m1 m2 by r square. And you know this gravitational force is a attractive force. And by using this equation, we can find out the corresponding potential, that is V equal to minus integral F. Here F is attractive force, therefore minus G m1 m2 by r square into dr. So we get V equal to minus G m1 m2 by r. Second example is electrostatic force. What is the force between two charges? That is F is equal to 1 by 4 pi epsilon 0 q1 q2 by r square. See, F is a function of r. That is why we are calling it as a central force. Here also F is a function of r. And third example is spring force. That is F is equal to minus kx. See, here we got the potential. So in this equation, it tells if we take the negative gradient of potential, we get the force. So I am going to check this equation. So I want to find out the force, that is I want to get this value F is equal to G m1 m2 by r square. So from this equation we know F is equal to minus del V. V is minus G m1 m2 by r. That is equal to, here del will be equal to minus dou by dou r into minus G m1 m2 by r. So what will you get? You get minus G m1 m2 by r square. This minus is because this force is attractive. The gravitational force is attractive. Here I forgot to put that minus sign. So see, by taking the negative gradient of potential, we can find out the corresponding force. An example problem. It is a problem of Sun-Earth system. Suppose this is a sun of mass capital M, and when we are drawing a sun, from nursery itself we will draw some lines like this. Ray. If some ray around a round circle, then it definitely will be sun. That is our understanding. So this is my sun. Okay. Now our earth is rotating around this sun, and its mass is small m, and he is rotating about the sun like this. You know, many girls are revolving around some boys. Maybe it is some attraction force, maybe it is a crush, or maybe it is love. So to revolve around some center, some attraction is required, right? And here in the case of Sun and Earth system, this attraction is gravitation. And suppose this is the radius r, then we know this gravitation attraction is minus G m by r square. And you please don't think the force of attraction, the gravitational force of attraction is only between Earth and Sun. It is there between you and your pen, you and your mobile phone, you and your laptop, and you and your room. Because yeah, everyone have this mass. So you have some mass, any other body have some mass. Okay, so it's a property of mass. The mass will attract each other, and maybe it is not obvious because the value will be very small. That is why you never feel this force of attraction, but you are connected to everything in the universe through your mass. In relativity, we will discuss the idea of gravitation through space-time curvature. So if you are a massive guy, then you will curve the space too heavily. And now I want to find out, and I already told you, the potential in the case of a gravitational force is equal to minus G mm by r. So this will be the potential in the gravitational force. Now I want to find out the Lagrangian. How to find out Lagrangian? Yeah, I already told you, if a particle is moving in a central force, then it will be a plane curve. That is r and theta. This is plane curve. The trajectory is plane curve, and this coordinate system is plane polar coordinate system. That is r theta coordinates. So here you know the general equation for kinetic energy in plane polar coordinate system. What is it? T is equal to half m r dot square plus r square theta dot square. And you know the potential energy, that is equal to minus g mm by r. So our Lagrangian will be equal to 1 by 2 m r dot square plus r square theta dot square plus g m by r. So for all the motion under gravitational force, the kinetic energy will be same, because gravitational force is a central force and the trajectory of a particle in central force is always a plane curve. So we can represent it by plane polar coordinate system. So in plane polar coordinate system, the kinetic energy is always 1 by 2 m r dot square plus r square theta dot square. Okay. Now a small work for you. Find out the generalized coordinates. Then find out the equations of motion. This one is a previous set question, and just now we derived the Lagrangian for a particle moving in gravitational force, that is 1 by 2 m r dot square plus r square theta dot square plus g m by r. Here in this problem, the particle of unit mass of the particle is unit, that is m equal to 1, and here g mm is called as k. So what is the correct answer? Yeah, it is option A, right? Now this one is another set question. You see, both the questions are same. The first question is asked in some year, and the second question is asked in another year. So you see, same question, almost the same question and same options they asked in multiple times. This is a common thing in set examination. So you can qualify the set exam very easily. Just go through all the previous question paper. Many of the questions will be repeated. One example problem. A force is given, that is f of r equal to minus k by r cube. Find Lagrangian and equations of motion. So here they given only the force, that is f is a function of r, and that is equal to minus k by r cube. They are not specified anything about the coordinate system. If we know the coordinate system, we can find out the kinetic energy. We know the general equation for kinetic energy in any coordinate system. But here in this question, nothing is mentioned. Then how we find out which coordinate system is the appropriate one? Here you see, this force is a function of r. If a force is function of r, I told you the trajectory will be a plane curve. Plane curve means r and theta. So our coordinate system will be plane polar coordinate system. And in plane polar coordinate system, you know the general equation for kinetic energy, that is 1 by 2 m r dot square plus r square theta dot square. So what is our Lagrangian? Lagrangian is equal to t minus v. We got what is the value of t. Now what is the value of v? How we can find out the value of v? I told you, if we know the force, then v of r will be equal to minus integral of f dr. So here they given the f of r, that is equal to minus k by r cube. So we can find out v by integrating this function, that is minus k by r cube dr. See, this minus minus will cancels and we get v is equal to k integral r raised to minus 3 dr. That is equal to k into r raised to minus 3 plus 1 by minus 3 plus 1. So what we get? V is equal to k into r raised to minus 2 by minus 2. So we get v is equal to minus k by 2r square. This is our potential. Now substitute this value here. So we get Lagrangian equal to 1 by 2 m r dot square plus r square theta dot square minus k by 2 r square. Now we got the Lagrangian, and I know you are very good in finding equations of motion. So do this by yourself. Here you see there are two generalized coordinates, one is r and one is theta. So solve this equation of motion for r and the theta. Okay. Another example problem, and it is a work for you. F of r is given, that is equal to minus k by r square plus k prime by r cube. Find Lagrangian and find equations of motion. Please do right now. Please pause the video and do the problem, then resume it. Okay. Otherwise, there is a chance for skipping these works. So don't skip. Please pause the video and do this problem right now. Here I am going to discuss a small concept. The relation between generalized force and generalized potential. Suppose the generalized force is u of qj dot. Here you can see there is a qj dot term, that is, it is a velocity dependent potential. And what will be the generalized force? The generalized force qj will be equal to d by dt dou u by dou qj dot minus dou u by dou qj. This one is a previous GATE question, and they are asked to find out the generalized force. Here the generalized potential is given. What is the generalized potential? V of q dot equal to 1 plus q dot by q square. Here I can rewrite this equation in two forms, that is 1 plus q dot into q raised to minus 2, and in another form, that is 1 by q square plus q dot by q square. This is just for less confusions. So here, what is the equation for generalized force? That is qj equal to d by dt dou u by dou qj dot minus dou u by dou qj. So first we have to find out dou u by dou qj dot and dou u by dou q. First one, what is dou u by dou qj? See, I am taking this equation. So dou u by dou qj is 1 plus q dot into minus 2 q raised to minus 3. And what is dou u by dou qj dot? I am taking this equation. So there is no q dot term, only here is q dot term. Okay, so what we get? We get 1 by q square. Now you have to substitute 1 by q square value here. So you have to take d by dt of 1 by q square and substitute this value of dou u by dou qj. So you get the answer. The answer is option C. Another concept, generalized momentum. What is this? If body is in a translation motion, then it is called linear momentum. And if a body is in a rotation motion, then the momentum will be called as angular momentum. And we know the Lagrange's equation of motion, that is d by dt of dou L by dou q dot minus dou L by dou q equal to 0. And I told you we derived the Lagrange's equation of motion from D'Alembert's principle, and D'Alembert's principle is based on Newton's equation of motion, that is F equal to ma. Or we can rewrite in another way, that is dp by dt equal to force. Now we just compare these two equations. So you can see this force is negative gradient of potential, that is dou L by dou q. So this time dp by dt is d by dt of dou L by dou q dot. So this time dou L by dou q dot is momentum, and this momentum we call as generalized momentum. That is generalized momentum Pi equal to dou L by dou Qi dot. And we know Qi dot is velocity, that is equal to dou L by dou V. So this is a important equation, Pi equal to dou L by dou Q dot. So for example, PR will be equal to dou L by dou R dot, and P theta will be equal to dou L by dou theta dot. Here this one is linear momentum and this one is angular momentum. See, this momentum is related to angle theta. So this is angular momentum and this is linear momentum. So generally we call Pi is equal to dou L by dou Q dot as generalized momenta. Okay. This one is a previous set question, and Lagrangian is given, that Lagrangian L equal to 1 by 2 m r dot square plus r square theta dot square minus v of r, and they are asked to find out the angular momentum of the particle. We know the equation for generalized momentum. What is it? Pi equal to dou L by dou Qj dot. Here we know Qj is generalized coordinate, right? And here we have two generalized coordinate, one is r and one is theta. So there will be two generalized momenta, one is corresponds to r and one corresponds to theta, that is Pr and P theta. What will be Pr? Pr will be equal to dou L by dou R dot, and what will be P theta? It will be equal to dou L by dou theta dot. And I told you this one is linear momentum and this one is angular momentum. Why? Because it is related to the angle theta, so it is angular momentum. So here the question is to find out angular momentum of the particle. So we have to take this equation. So what is dou L by dou theta dot here? It is equal to m r square theta dot. So option B is the correct answer. And here what will be the linear momentum here? It will be equal to dou L by dou R dot. That will be equal to m r dot. Now a small work for you. You know the Lagrangian in spherical polar coordinate system. What is it? 1 by 2 m r dot square plus r square theta dot square plus r square sine square theta phi dot square minus v of r. Here you know generalized coordinates are r theta and phi, because these people have bindi. Okay, so there will be corresponding momentum, that is PR, P theta and P phi. So your work is find out these values. I think you know the equation, that is generalized momenta Pi equal to dou L by dou Qi dot. So please solve it. This one is a net problem. And here the question is to find out canonical momentum PR. So we know PR equal to dou L by dou R dot. And here Lagrangian L is given, that is L equal to x dot y dot minus x square minus y square. But the problem, you see, in the given Lagrangian there is no R dot term. Then how we take the derivative? But in the question they are told us in polar coordinate system. See, they are asked to find out it in polar coordinate system. So we have to convert this x and y to polar coordinate. What is polar coordinate system? Suppose this is x and this is y, and if this is r and this is theta, then x will be equal to r cos theta and y will be equal to r sin theta. So what we have to do? We have to take x dot, y dot, and then we have to substitute all these values in the given Lagrangian. So what is x dot? X dot will be equal to r dot cos theta minus r sin theta theta dot. And what is y dot? It is r dot sin theta plus r cos theta theta dot. Now I am going to substitute all these values in the given Lagrangian, that is L equal to x dot y dot, that is r dot cos theta minus r sin theta theta dot into y dot, that is r dot sin theta plus r cos theta theta dot minus x square, that is r square cos square theta minus y square, that is r square sin square theta. Now you please do this multiplication, so you get a Lagrangian, and then use this equation, that is PR equal to dou L by dou R dot. You get the answer, and the correct answer is option D. So please do it by yourself. Here, to solve this problem, the following two equations might help you. That is 2 sin theta cos theta is equal to sin 2 theta and cos square theta minus sin square theta equal to cos 2 theta. So to get the final answer, you have to substitute these values in between the mathematical manipulations. Okay, then you get the option D. This one is a previous gate problem, and if you're remembering the gauge invariance of Lagrangian, the idea I already discussed in the Lagrangian part 2 or Lagrangian part 1. So if you're remembering the gauge invariance of Lagrangian, then you can easily exclude these two options. How? Here see, equation of motion changes. Maybe you forgot about gauge invariance of Lagrangian, right? Don't worry, I tell you. What is this gauge invariance of Lagrangian? I told you, if we modify a Lagrangian, that is, we are adding an integrable function to the Lagrangian, that is L plus df by dt. So we get a new Lagrangian L prime. But When we take the equation of motion will not change. By adding an integrable function. That is gauge invariance. See, d by dt is a differential. So we can integrate this function. So what we get? We get f. So this is a df by dt is a integrable function. Similarly, you see in the given Lagrangian, see this one is L0 and to this L0 we added a term, that is a integrable function. So the equation of motion will not change. So we can exclude option C and option D. Now we have to find out the canonical momentum for both the Lagrangian. And you know how to find out the canonical momentum. So you please do and find out the exact answer. A small note. We know the Lagrangian equation of motion is d by dt dou L by dou q dot minus dou L by dou q equal to 0. And I told you dou L by dou q dot is nothing but pi. That is d by dt of pi minus dou L by dou q equal to 0. And what is d by dt of pi? That is pi dot equal to dou L by dou q. And from this equation, you can see pi equal to dou L by dou q dot. Okay, so we got two equations. One is pi dot is equal to dou L by dou q and another is pi equal to dou L by dou q dot. See, here it has a bindi and here there is no bindi. And here there is no bindi, but here there is bindi. So these are husband and wife. Wife and the husband. Here this is husband and this is wife. And in most of the cases, if one is dominant, then other will be suppressed. So here wife is dominant, so husband is suppressed. It is inversely proportional. Okay. Okay, so please don't forget. Okay. So very important. Not husband and wife. These equations are very important. Okay. Another concept, cyclic coordinates. Let us consider an example. A Lagrangian L is equal to 1 by 2m r dot square plus r square theta dot square minus v of r. This is a Lagrangian corresponds to central force, right? Here, what are the generalized coordinate? You know, the generalized coordinate will have bindi. So r is a generalized coordinate and theta is also a generalized coordinate. Now you can see this generalized coordinate is present in the Lagrangian. Here r square theta dot square. So there is r and this theta is absent in the Lagrangian. If the velocity is present but the corresponding generalized coordinate is absent, then we call it as a cyclic coordinate. So here the cyclic coordinate is theta. This is the missing coordinate. See, check the Lagrangian. There is no theta term. But there is a velocity, theta dot is there. The velocity corresponds to that theta is there, but that coordinate is not there. So such coordinates are called cyclic coordinates. Now another example. Lagrangian L is equal to 1 by 2 m r dot square plus r square theta dot square plus r square sine square theta phi dot square minus v. Here what are the generalized coordinates? See, this one have bindi. So r is a generalized coordinate. And you can see this r in the Lagrangian also. And theta is also a generalized coordinate. And you can see this theta in the Lagrangian. Now, this is also a generalized coordinate, that is phi, but you can see that term in the Lagrangian. So here the cyclic coordinate is phi. That is the missing coordinate in the Lagrangian. So the cyclic coordinate is the missing coordinate. Okay. That is Lagrangian doesn't depends on cyclic coordinate. See, this one is a previous set question. And what is the answer? Yeah, I know you don't want my help, right? Okay. Next concept, constant of motion. What is it? We know the Lagrange's equation of motion is d by dt dou L by dou q dot minus dou L by dou q equal to 0. And we know the Lagrangian L is generally a function of q, q dot and t. But if q is cyclic coordinate, then Lagrangian will be function of q dot and t only. That I already told you, if a coordinate is cyclic, then that coordinate will not be there in the Lagrangian. That coordinate will be absent in the Lagrangian. Okay, so here you see dou L by dou q. When we are taking derivative of Lagrangian with q, but here you see there is no q term. So what we get? We get this is equal to 0. So we get d by dt dou L by dou q dot minus 0 equal to 0. When we get derivative of function equal to 0, for example, if you are taking time derivative of a constant value, that is 2, what is its value? It will be equal to 0. And if you take a time derivative of 10, what we get? Equal to 0. Therefore, time derivative of a constant is equal to 0. Why we are calling some quantity as a constant? Because it will not change with respect to time. That is why we are calling it as constant. Okay. So, here you see this term dou L by dou q dot is a constant. And you know dou L by dou q dot is P. Are you remembering? So, P is a constant. That is, it's a small note. The generalized momentum corresponds to cyclic coordinate. Is constant of motion. It's an important point. Okay. Here I tell you some examples. Suppose our Lagrangian L is equal to 1 by 2m r dot square plus r square theta dot square minus v of r. Here what are the generalized coordinates? One is r and other one is theta. And you can see r is here and there is no theta. Theta is absent. That means it is a cyclic coordinate. That is, theta is a cyclic coordinate. And we know the generalized momentum corresponds to cyclic coordinate is constant of motion. Then what will be the generalized momentum corresponds to theta? That will be p theta. Then p theta will be constant of motion. And we know p theta equal to dou L by dou theta dot. So what we get? We get m r square theta dot. And this value will be constant of motion. That is, this value will not change when the body is in a motion. That is, this quantity is independent of time. Always it is same. A simple work for you. The Lagrangian is 1 by 2 m rho dot square plus rho square phi dot square plus z dot square by 1 plus rho by lambda all square minus v of rho. Find constant of motion. Here what are the generalized coordinates? Rho is there, phi is there, z is there. But what are the cyclic coordinates? Only phi and z. So you get two constant of motion. One is corresponds to p phi and one is p z. So please solve it. This one is a previous gate problem. And the question is to find out the canonical momentum and check whether it is a conserved quantity or not a conserved quantity. Here, look into the Lagrangian first. In the Lagrangian, what is generalized coordinate? Q dot is a generalized coordinate. That is, Q is a generalized coordinate. And you check this Q is there. So, Q is not a cyclic coordinate. Okay. The generalized momentum corresponds to cyclic coordinate only will be constant of motion or conserved quantity. And here the question is to find out the correct statement. So which of the options are correct? PQ is not a conserved quantity because Q is not a cyclic coordinate. So PQ is not a conserved quantity. So here also it is not a conserved quantity. So these two options are wrong. Now we have to find out the value of PQ. See, that is not a big deal. You know what is PQ? PQ is equal to dou L by dou Q dot. And what is it? You get 2 alpha Q dot. So the answer is option D, right? This one is another gate problem. And the question is to find out the conserved quantity. So to find out the conserved quantity, first we have to find out the cyclic coordinate. So to find out the cyclic coordinate, first we have to identify the generalized coordinate. So here this is a generalized coordinate, but theta coordinate is there. So it is not a cyclic coordinate. And this one is another generalized coordinate. And you see there is no phi term in the Lagrangian. So this one is a cyclic coordinate. So the corresponding momentum will be constant of motion. So p phi will be the constant of motion. What is p phi? P phi is dou L by dou phi dot. So what you get? Find out. I tell you the answer is option A. This one is a previous set problem and you please find the answer. Simple one. This one is another gate problem. The question is to find out momentum conjugate to R is. But here the difficulty is they didn't given the Lagrangian, but they given the figure. So we have to construct the Lagrangian, then only we can find out the momentum conjugate to R. Actually, we solved the Lagrangian for this problem earlier. Are you remembering? Look into the problem. This problem has certain symmetry. Which symmetry? It have a cylindrical symmetry. So if there is a cylindrical symmetry, then the kinetic energy of Lagrangian will be equal to 1 by 2 m r dot square plus r square theta dot square plus z dot square. I told you to remember this equation. So what will be the Lagrangian? T minus v. Okay, so you can easily find out the Lagrangian. Or you can use our superposition method. So what is superposition method? We have to find out the velocities, then we have to add the velocities. Here you can see the bead is sliding down. So there will be a velocity in this direction, that is z dot. And there is a velocity in this direction. And there is a velocity in this direction. Okay, so you just add these velocities, you get the Lagrangian. But here it is easy to write the Lagrangian based on its symmetry. So here the Lagrangian is L equal to T minus V, that is 1 by 2 m r dot square plus r square theta dot square plus z dot square minus mg r cos 45. So we got the Lagrangian and we have to find out momentum conjugate to r, that is PR. PR is equal to dou L by dou r dot, that is equal to mr dot. It's a very simple question. Concept: determination of constant of motion from potential energy. How we can determine the constant of motion if only the potential energy is given? If kinetic energy is also given, then we can find out which are the generalized coordinate. The generalized coordinate will have bindi, right? But here in the question they are given only potential energy. So we cannot easily find out the generalized coordinate. Then how we find out the constant of motion? You know, d by dt of dou L by dou q dot minus dou L by dou q equal to 0. This is Euler-Lagrange equation. And if this q is a cyclic coordinate, then dou L by dou q will be equal to 0. Then we can say this term, that is dou L by dou q dot, that will be equal to p. It will be constant of motion. That is, it will not change during the motion of the system. Example problem. In a problem, only potential is given and it is equal to v of x, y plus a, z plus b and t. That is, this potential is a function of x, y, z and t. And the question is to find out constant of motion. See, here we cannot find out the generalized coordinate easily. Why? Because only potential is given. In kinetic energy only the coordinate with the dot, that is bindi. Here only coordinates are there. So here from this potential itself we cannot find out the generalized coordinate, right? That is a difficulty. Then how we solve this problem? In the earlier class I told you about one concept, that is homogeneity of space. What is it? That is, if we take a y coordinate and we translate it to some other position, that is y plus a, then the momentum corresponds to y coordinate, that is py, is conserved. And if z is translated by z plus b, then the corresponding momentum, that is pz, is conserved. This is a direct consequence of homogeneity of space, that is linear momentum is conserved. We already discussed this idea, right? So here Py will be conserved quantity, that is Py is a constant of motion, and here Z is a conserved quantity, so Pz is a constant of motion. And you can see the equation of potential is explicitly depend on t, that is in the equation of V we can see the t coordinate. If there is explicit time dependence in the potential energy, then energy is not conserved. Here I am going to summarize this idea. That is, we have a potential, that is V equal to V of x, y plus a and z plus b and t. And you can see there is a constant time, that is a. If there is a constant time, then the associated coordinate and its associated momentum, that will be Py, will be constant of motion. And see here z plus b, so b is a constant. Then the corresponding coordinate and its corresponding momentum will be constant. And if you can see an explicit time dependence, that means you can see the t coordinate in the equation, then energy is not conserved. That is, if V is a function of t or V is a function of velocity, potential energy is function of velocity, then energy is not conserved. And if V is a function of r only, then energy is conserved. I give you some explanation. You are very much familiar with the gravitational force. So suppose I am throwing a ball from ground to certain height. So initially it is kinetic energy is maximum. I am throwing with the initial velocity. So kinetic energy will be maximum. So the total energy here will be kinetic energy only. And when this ball reaches its maximum height, the total energy will be equal to its potential energy. That is, this kinetic energy is converted to potential energy. And in between any position, the total energy E will be combination of kinetic energy plus potential energy. That is, this term is constant in this motion. Here, initially it have complete kinetic energy, and when it reaches maximum height, the complete kinetic energy is converted to complete potential energy. So the conversion of energies happen, but the total energy is constant. And you know this potential energy is equal to mg h. H is the position coordinate, right? Now check these two ideas. First I'm checking this one. I told you V is a function of r, position only, then E is conserved. Here you see this potential is a function of h only, that is positional only. So it is a conserved, and you know this motion is under gravitational force field, and gravitational force field is a central force. Central force means it depends only on position. Okay. Now I'm going to check this first concept, that is, if potential is a function of velocity, then what will be the E? Suppose for this case, here you know velocity is maximum, and here you know velocity equal to minimum or 0. So suppose this potential is function of velocity, then what we will get? We will get maximum kinetic energy at this position and the maximum potential energy at this position. And at this location we get minimum kinetic energy and the minimum potential energy. So here in this motion, the total energy is not conserved. It is not constant. When it is at the ground, the energy will be maximum. And when it is at the maximum position, the total energy will be 0. Okay. So here you can see the energy is not conserved. So if potential is a function of velocity, then energy is not conserved. No need to remember all those things. You just remember these two ideas. Okay, that is sufficient to solve problems. One example problem. Lagrangian is given and it is equal to mx dot square minus v of r t. Then find conserved quantities. Options are, first one L, option 2 E, option 3 L and E, option 4 none of this. What is the answer? Here you see the potential is function of time. So energy is not a conserved quantity. And here you see potential is a function of r. Then which quantity will be conserved? Angular momentum will be conserved. Why? If v is a function of r, that means it is a central potential, and in a central potential angular momentum is conserved. Okay, maybe you have this doubt, why angular momentum is conserved under a central potential? Don't worry, I will tell you. Here, suppose there is a particle is there and the force acting on this particle is 0. And you know F is equal to dp by dt, that is rate of change of momentum. So that is will be equal to 0. When time derivative of function is 0? When that quantity will be a constant. That is here p is a constant value. Right. That means linear momentum is conserved if the force is 0. Now I am going to consider a central force. You know, from central potential we can find out central force. So if there is a central force is there, then the corresponding potential will be central potential. Gravitational force is a central force and the corresponding potential is central potential, right? So I am taking the gravitational force. So two masses are there, one m1 and other m2, and the distance between them is r. Then the force will be equal to g m1 m2 by r square. Here you can see the direction of force is acting in the same direction as the position vector. That is, the angle between force vector and position vector is equal to 0. Here in the case of a central force, what will be the rotational force? Is there any rotational force? That is torque, right? And torque is equal to r cross f, that is rf sin theta. And here we got the angle between force vector and the position vector is 0. Therefore theta will be 0. So sin theta equal to 0. So this is equal to 0. That is torque acting under central force is 0. And we know this torque equal to dl by dt. L is angular momentum. And we already find out that for a central force, this torque will be equal to 0. That means L vector is equal to a constant. L is angular momentum. That is why I told you, if the potential is a central potential, then the force will be central force, then the angular momentum will be conserved. Please write down this. A particle moves in a potential x square plus y square plus z square by 2. A particle moves in a potential x square plus y square plus z square by 2, and which component of angular momentum is constant of motion? This is the question. So here the potential is given, that is V equal to x square plus y square plus z square by 2. Here you can see, if a particle is moving in a x direction, there may be a momentum px, and if it is moving in a y direction, there will be a momentum py, and if it is moving in a z direction, there will be a momentum pz. But here, these are linear momenta, right? All are linear momentum. But in the question, they are asked to find out angular momentum. Then how we find out the angular momentum? Here all the coordinates are just position coordinate x, y, z. There is no angle coordinates. Then how we find out the angular momentum? That's the question. So what we have to do? We have to convert the coordinate system. Here this coordinate system is Cartesian coordinate system. If we convert it into a spherical polar coordinate system, that is r, theta, phi. So there will be corresponding p theta and corresponding p phi. So we can find out these values. And what is p theta? P theta will be equal to dou L by dou theta dot. And what will be p phi? It will be equal to dou L by dou phi dot. So you can easily find out. Therefore, what we have to do? We have to convert this potential in spherical polar coordinate system. So what will be the potential in spherical polar coordinate system? So here we have to know the relation between xyz coordinate and the r theta phi coordinate. What is the relation between them? I told you this in the earlier class. Are you remembering? The x will be equal to r sin theta cos phi, and y will be equal to r sin theta sin phi, and z is equal to r cos theta. So you can substitute these values, x, y, z values in this equation. So we get the potential. But to find out the generalized coordinate, we have to know the Lagrangian. Then what will be the Lagrangian here? That is t minus v. So Lagrangian will be equal to, see, what is the kinetic energy, general form of kinetic energy in spherical polar coordinate system? It is equal to 1 by 2 m r dot square plus r square theta dot square plus r square sin square theta phi dot square minus v. What is v? V is equal to x square plus y square plus z square by 2. So we have to substitute these values of x, y and z in this equation. So what we get? X square, that is r sin theta cos phi all square plus y square is r sin theta sin phi all square plus 1 by 2 z square, that is r square cos square theta. Here you can see this and these are common terms. So we can take it outside, and what we get? R square sin square theta into cos square phi plus sin square phi. So we can write the Lagrangian as 1 by 2 m r dot square plus r square theta dot square plus r square sin square theta phi dot square minus r square sin square theta minus 1 by 2 r square cos square theta. Now we have to identify the generalized coordinates. What are the generalized coordinates? R is a generalized coordinate, and another is theta is a generalized coordinate, and phi is a generalized coordinate. Then what are the cyclic coordinates? Check. Is this r is present in the Lagrangian? Yes. So it is not a cyclic coordinate. Check. Is theta is present in the Lagrangian? Yes. So it is not cyclic coordinate. And check phi. Is anywhere phi is there? No. So the cyclic coordinate is phi. Then the corresponding momentum will be constant of motion. So in this case, P5 will be the constant of motion. And what is the value of P5? P5 is equal to dou L by dou phi dot. Find out this value. So work for you. Here sometimes I call this quantity P5 as angular momentum. But it is wrong. Actually the angular momentum L equal to, we know, R cross P. Right. And this is the exact definition for angular momentum. Here the P is P5 and the corresponding L will be the component of Lz. Here you know this L is a vector, that is L vector is equal to I Lx plus J Ly plus K Lz. So the Lz component of angular momentum is conserved in this problem. Okay. This one is a previous CSIR net problem. So see, this is a lengthier question. So when reading this question, please remember the important points. Here, in this question, the Lagrangian of a system moving in 3 dimensions. This is an important point. And the Lagrangian is given. And then the independent constants of motion are. One is energy, another time is linear momentum, another time is angular momentum, and constant of motion. So these are the main points in the question. So first, you look into the Lagrangian. This Lagrangian is not familiar for you. Here, this Lagrangian is in terms of x1 dot square, x2 dot square, x3 dot square. So what is this x1, x2 and x3? Then how we can relate this x1, x2 and x3 to linear momentum and angular momentum? That is why this term is important. 3 dimensions. So in 3 dimension, what is the coordinate? You know, x, y, z are the coordinates in 3 dimension. So in this question, x1 is corresponds to x, x2 is corresponds to y, and x3 is corresponds to z. So now we can rewrite this Lagrangian, that is L equal to 1 by 2 m x dot square plus m y dot square plus z dot square minus 1 by 2 k x square minus 1 by 2 k y plus z whole square. So now the Lagrangian is something more familiar to us, right? Here the actual procedure of solving this problem is like this one. First we have to check dou h by dou t. If this value is equal to 0, then we can say energy is conserved. Here h is Hamiltonian and it is equal to L plus V, and if there is a Lagrangian, we can convert it into Hamiltonian. I will tell how we can convert Lagrangian to Hamiltonian in the next lecture. So anyway, first you have to find out the corresponding Hamiltonian. Here the corresponding Hamiltonian you get as h equal to px square by 2m plus py square by 4m plus pz square by 4m plus half kx square plus half k x plus y all square. Now you have to do this partial derivative, that is dou h by dou t. So you get it is equal to 0. So in this problem energy is conserved. Now we have to check the second condition, that is dlx by dt equal to lx h plus dou lx by dou t. If this is equal to 0, then it is conserved. The Lx will be conserved. And if it is not equal to 0, Lx is not conserved. So you have to check for dou Ly by dou t and the dou Lz by dou t. Then only you can find out which are the conserved quantities. And here I tell you this Lx will be equal to y pz minus z py. And similarly you can find out Ly and the Lz. Then substituting in this equation, then you can find out which are the conserved quantities and which are the non-conserved quantities. But see, to solve in this proper way, it is time consuming and it take one rough page completely. So this is not a practical method. So how we can solve this problem? Yeah, I tell you the trick. The trick. But to use this trick, you have to remember the following things. First one, if Lagrangian is independent of time, that is explicitly independent of time, then total energy will be constant of motion or conserved. Second one, if the given potential V is equal to x square plus y square plus z square by 2, then which one will be the conserved quantity? You see, here x square and y square, its coefficients are same. Then the other quantity, what is other quantity? Z square by 2. And the corresponding generalized momentum will be constant of motion. Or that will be conserved quantity. Third one, if the potential is V equal to 1 by 2 x square plus y square plus z square. Here see, the coefficient of x square is 1 by 2, y square is 1 by 2, z square is 1 by 2. All are same. So what is the other quantity in the potential? There is no other quantity in the potential. So generalized momentum will be not conserved. Fourth one, if the potential V is equal to 1 by 2 omega square x square minus alpha x raised to 4. Here see, nothing is same. Then none of the generalized momentum is constant of motion or conserved. None of. Okay. So if you know these examples, then you can easily solve the problem. Now we are going to solve the CSIR net problem by using our trick. See, here first you have to check whether energy is constant of motion or not. So what is the trick? If L is independent of T, then it will be the energy will be constant of motion or conserved quantity, right? Now we have to check is linear momentum or angular momentum is conserved or not. So to use our trick, we need to know the potential. Here the potential is equal to half k x1 square plus half k x2 plus x3 whole square. This is equal to 1 by 2 k x square plus 1 by 2 k y plus z all square. Now I am going to expand this term, that is equal to 1 by 2 k x square plus 1 by 2 k into y square plus 2 yz plus z square. That is equal to 1 by 2 k x square plus 1 by 2 k y square plus k yz plus 1 by 2 k z square. Here I am rearranging this equation, that is 1 by 2 k x square plus 1 by 2 k y square plus 1 by 2 k z square plus k y z. Here you can see these terms are same. If these terms are same, then the other coordinate, the momentum, generalized momentum corresponds to other coordinate will be the conserved. That is, I told you in the trick. But here you see there is a cross terms. Two coordinates are there, one is y and one is z. So we cannot say py component of momentum is conserved or pz component of momentum is conserved. We can say that thing. Therefore, none of the component is conserved quantity. Component of generalized momentum is a conserved quantity. In the coming classes, I will discuss how to convert Lagrangian to Hamiltonian and Poisson's brackets. So you can solve this problem by using the proper method. Okay, this is a work for you. After some classes, you please come back to this problem and solve properly and check whether this trick is working or not. Okay. So for this question, option A is the correct answer. Only energy is conserved.